texture. So texture with rocks has a slightly different meaning than it does with minerals. Minerals, it literally is how it feels. Texture in terms of rocks refers to the size, shape, and distribution of the crystals or grains that make up a rock. So some examples include fine grain, like our rhyolite here. Coarse grained, like our granite. So coarse grained, you can usually see individual little speckles in there, different mineral crystals. Or glassy, such as our obsidian over here. And glassy basically meaning there are no crystals in this. So again, rhyolite is fine grained, so it has very small crystals. Granite is coarse grained, so it has larger crystals. You can see some of the dark spots here and light spots. And then obsidian, which is glassy. It has no crystals. And then crystal size and cooling rate. So extrusive rocks like rhyolite and obsidian cool rapidly, so there's not enough time for large crystals to form. Sometimes this happens so quickly that no crystals form at all. And this results in volcanic glass like obsidian. So glass, technically the definition of a glass is it's a solid in which the atoms are all randomly arranged. So it's volcanic glass because the atoms and that make up the obsidian are all randomly arranged. It's still solid, yes, but they're not formed in any kind of crystals. Remember, crystal has a repeating structure to it. When magma cools below the surface, there is sufficient time for large crystals to form. So we have sort of a generic graph here. So cooling time, so less cooling time to more cooling time, going this way. So our time is increasing. Going that way. Our crystal size is sort of increasing up the y-axis here. So if you have less cooling time, in fact, if you have very little cooling time, you'll have no crystal size. There will be no crystals. It's glass. The more time that you have for crystals to form, the larger the crystals are going to be. And then porphyritic rocks. So porphyritic texture is characterized by large, well-formed crystals surrounded by finer grained crystals of the same mineral or different minerals. So you have something like this over here. You've got these larger crystals in here, and they're surrounded by this darker mineral here. This does indicate a complex cooling history. So it begins cooling slowly, which allows time for these large crystals to form, like these crystals down here. So it cools slowly and have time for these larger crystals to form. Then it suddenly cools. So maybe it may be magma that's underground for a long time that cools slowly and then erupts out of the volcano suddenly. And when it does that, then it starts to cool rapidly. So that would form all this material that's surrounding those large crystals. So this can occur if a magma body cooling slowly deeper in the earth is suddenly forced upward or erupts onto the earth's surface, leading to rapid cooling of uncrystallized magma. So it's this here. But again, we call that a porphyritic texture. Vesicular rocks, or a vesicular texture. So magma contains dissolved gases that escape when the pressure on the magma is reduced, just like taking the lid off of a bottle of soda. If the lava is highly viscous, which means it's very thick, it doesn't flow very easily, those gas bubbles may not be able to escape, and that leaves holes called vesicles behind. So you have something like this vesicular basalt up here, or pumice. So it looks kind of spongy, actually. It's got a bunch of holes in it. So this does result in a spongy looking rock. We call this a vesicular texture. Okay, and a vesicular texture is basically a rock that has a spongy appearance. So that's the term we use to describe the spongy appearance. And the holes themselves are actually called vesicles. So igneous rock identification. So you kind of use this chart to identify igneous rocks. So you kind of look at the rock and decide first off, up here at the top, what color is it? Is it light colored? Is it granitic because it's light colored? Is it darker and basaltic, etc.? So that gives you an idea of where it kind of falls on that scale. So again, lighter colors on the granitic side, darker colors on the basaltic side. And then this here is kind of just showing roughly what minerals may be in there. So if it's granitic, for example, you can have muscovite, mica, quartz, potassium, feldspar, a little bit of amphibole, maybe a little bit of plagioclase, feldspar, biotite. So you end up with a lot of different minerals possible in these granitic rocks. You get over to intermediate, it's more plagioclase. There is some potassium, feldspar, pyroxene, amphibole, biotite. The basaltic rocks, you're mainly looking at pyroxene and olivine making up most of that, and plagioclase, feldspar, a little amphibole. And then by the time you get to ultramafic, it's basically olivine and pyroxene. Okay, so but this kind of gives you an idea of what minerals would be in there. But you kind of start by looking at it. Is it light? Is it dark? And then look at the texture. Is it coarse grained? Is it porphyritic? Is it fine grained? Is it glassy? Is it vesicular? Etc. So, for example, if it's porphyritic and it's light colored, so it's probably this porphyritic rhyolite or granite. If it's, say, dark colored and coarse grained, it's going to be gabbro. If it's an intermediate color and it's fine grained, it's going to be andesite. If it's lighter in color and vesicular, it's going to be pumice. If it's darker in color, like a reddish brown, it's scoria. So anyway, you kind of use this to identify some of your igneous rocks.